Forensic science, two words that ignite those murdery mystery craving minds. But did you know there is more than meets the eye? Mathematical functions, specifically polynomial functions, something that looks like this. But basically, a polynomial is a sum of a group of terms containing variables with whole number exponents. Today, I'm going to introduce to you a model that could give you the answers you need when it comes to the mystery genre. Say hello to As you can see in the graph, both the domain and range is from negative infinity to positive infinity. This will always happen unless there are some restrictions. Another thing that you might notice here is that there are certain points where the function rises and falls. It's hard to determine the exact number, but the function rises from negative infinity to at some point between negative 5 and negative 4. It falls from at some point again between negative 5 and negative 4 to a point between 0 and 1. Then it rises from that point to positive infinity. These are the turning points of the graph. But did you know that the highest power in the function, or the degree, which in this case 3, has a relation with the graph? But how? The turning points are 1 less than a degree. Since we have 3 as a degree, there are 2 curves. These are also where our relative extrema are. Our relative maximum is the highest point, or in this case at t equals negative 4.38. And the relative minimum is the lowest point, or in this case at t equals 0.38. Now, let's move on to its intercepts. We can get the intercepts by replacing y or x with 0, depending on what we're looking for. Let's try looking for the y-intercept by replacing x with 0. We will get 0.8, or in interval notation, 0, 0.8. For the x-intercept, we're going to replace y with 0. This is where it gets complicated. We have to use a rational root theorem to solve this and try numerous numbers to check if it is a solution to the function. But to make it short, as you can see in the graph, it crosses the x-axis in between negative 6 and negative 7, or around negative 6.89. That will be our x-intercept. Now, you may be wondering, shouldn't the graph cross 3 times? The degree of the polynomial is 3, right? Shouldn't that tell us about how many solutions are there to a function? Sometimes, the roots or the zeros of polynomial functions can be imaginary or non-real. For this function, the other 2 I didn't mention aren't real, so they won't cross the x-axis. By now, you might be looking for the asymptotes. Well, good news, there is none. One thing off from the things we need to worry about when solving these kinds of functions. This is because they are continuous and defined for all real numbers, which means there are no undefined points for vertical asymptotes, and the graph doesn't approach a specific line as x approaches infinity or negative infinity, so there are no horizontal asymptotes. But what about the inverse? In solving the inverse, we must first know if it's a one-to-one function or not by doing the horizontal line test. A function is one-to-one if each y value in the range corresponds to exactly one x value in the domain. As you can see, the line has touched the graph more than once, meaning this is not a one-to-one function, so it doesn't have an inverse. In conclusion, polynomials are more than just algebraic expressions. They are tools that allow us to model and solve problems in the world around us. From the domain and range, to intercepts, to graphs. Understanding polynomials helps unlock new insights into everything. So the next time you see a curve or solve a complex equation, remember that it's polynomials at work.